My name is Lior. This is a tutorial intro to C++ 11.14. Third year I've done this type of talk here. It keeps evolving. This year there's more C++ 14 stuff, and there's not even going to be an attempt to cover the libraries. So we're just going to look at the language, and I think that'll be plenty to fill 2 sessions. So it's this session and then the session after lunch here. We'll be back. So here's what we're going to cover. We'll start with the C++ required history briefly. What some of the goals are for the new C++, which is kind of how I refer to be efficient to everything from C++ 11 forward. And we'll look at simpler language features first, the ones that are fairly straightforward. And that's really all going to be this session. And then in the afternoon session, we'll do the other 2 parts. Same number of slides, much smaller number of topics because they get more elaborate. So new facilities for class design and initialization, move semantics, lambdas. So I try to at least mention just about every language feature that I'm aware of. There's at least a line on it somewhere. Not a whole lot of gory detail on some of it. So the code that you see has been tested on several versions of TDM, which is a nice version of GCC you can get that comes with a Win32 installer. And originally I used Michael Williams' threading library for the threading stuff, which isn't even in this talk, so I don't even know why I'm telling you about that. All the examples are not necessarily compilable as you see it on the slides, though, because I cut off things like includes and qualifiers for namespace just to make them fit. But aside from that, it should compile. So this is a great slide. I'm sure a bunch of you have seen it. It's kind of been making the rounds. Herb Sutter first published it in his trip report from the ISO C++ meetings. And it just kind of gives you a nice visual of the history of the language. Of course, C++ 98 was first standardized in 98. And all this time, from 98 to 11, the language was evolving into this major language update. So right around 03, C++ 03 came along, trivial, just bug-fixed update, basically. The most significant thing to happen officially in this whole period is the release of the library TR, which was actually known as TR1. And TR1 introduced a whole bunch of new features of the library, not the language, that were eventually going to be in C++ 11. So of course in C++ 11, finally it was official, and the language features that they've been working all this time were made official. And all these facilities from TR1 were now able to be recoded using the C++ 11 language features, so it made them all more efficient, more functionality, etc. And now we're in this period here where the Standard Committee has gone to a new sort of approach to things, which is to come up with these technical specifications for features, not necessarily tied into a particular major or minor release from the Standards Committee, but it allows these various working groups to think about and polish various library and language facilities, and then eventually they make it into one of the official language releases. So C++ 14, I believe, has been pretty much fixed, although it hasn't been officially ratified, so we know exactly what's in that. The next, Herb calls it major update of the language will be C++ 17. There's nothing about that in here. I have no idea what's in that. So, brief history of time. What were the goals for C++? Make the language easier to teach, learn, use for everybody. Of course, always maintaining backwards compatibility is important. And it's not 100%. Of course, there's certain things that are breaking changes in C++ 11. We'll talk about a few of them. Improve performance. That's always a good thing. Strengthen library building facilities, which are called tools for class design here in this talk. And the last item, which is described sometimes, interface more smoothly with modern hardware. It's really just code speak for support multi-threading, because modern hardware is moving to multiple cores. There's an incredibly great talk by Herb, Why C++, I highly recommend everybody who hasn't seen that talk, Google it and watch it, like 45 minutes. He gave it as the keynote for the Banff in 2011 C++ and Beyond seminar. And he actually gave the talk 2 days before C++11 was actually ratified. So the timing was really good. And it's a great survey of C and C++ over the years, why it was popular, why the coffee-based languages kind of took over in the first decade of the century, and then native code is making a renaissance. So definitely recommend that. So we'll quote from Bjarne: the pieces of C++11 just fit together better than they used to, and I find a higher style level of programming more natural than before and as efficient as ever. Understatement there from Bjarne, it's really more efficient. All right, so here's the first section. This is what we're going to talk about, and I'm just going to go do it. So I forgot to say that the approach I try to use here as much as possible is show C++98, old C++ code, what's wrong with it, and then show how C++11, 14 improve upon it. So we'll start with pure old C++ function. We won't call this an algorithm because it doesn't take a range. It's just a function template that takes a reference to a container of some kind and it searches it for the first null. So there's an assumption that's full of pointers. And it returns in the STL-like manner an iterator to the first null pointer that it finds or the end iterator, another STL convention. All right. So it's a reference to a const. We need a variable in here to iterate, so we have to declare it. So right away, things are really kind of wordy here, right? Type name, container, : const iterator, it. Why is all this necessary? Why is the type name necessary? It turns out if you want to refer to a name in a template that's dependent on a template parameter, the compiler, without this type name here, can't really tell, because it, at least in the first pass of compiling, because templates are compiled twice, two-phase translation, right? The first time when the compiler first sees the template source code, and then the second time when it's specialized. So when the compiler first compiles this, it doesn't know what this class actually is, and it doesn't know what this member is. So it could be the name of a member, it could be the name of a type. And if you don't specify, the rule is it's supposed to assume it's the name of a member, which would make this bad syntax, and you get a syntax error if the compiler is being strict. For years, compilers just ignored that and figured out what you really meant, which is really bad, because then the code would stop working when compilers got more conformant. All right, so you have to say type name. So we're going to iterate across this container. First null, dereference each iterator. If we find null, we're done. Otherwise, we end up returning the end iterator. So not real exciting, but there it is in old C++. How about using this? So here's a piece of user code just set up to exercise that function, kind of the minimal test. We stuff a vector full of pointers. And in old C++, there was no really convenient way to initialize a vector with some fixed values. So we have to take the address of each int in this case and stuff it in with pushback. All right. Then we call the function and capture the result. Well, the result is a const iterator for that container type, so we're kind of obliged in old C++ to write that all out. Kind of verbose. And then we just work with it. So one of the things we want to do is, if we actually get back a non-end iterator, we want to display the position of that null that we found as an index number. It was index position number 4 or whatever. So to do that, technically, to be completely kosher, we have to declare the result of subtracting two iterators as the difference type for that particular type of iterator, or for that type of container. So vector of int pointers has a difference type, and that's what you have to declare, or you're supposed to declare. The result of subtracting two iterators. Is this actually necessary? What would happen if I just said size t here? it would probably work. Right? I'm not aware of any platform where size T would fail in this case. But the designers of the STL were very forward-looking here, and they said, well, yeah, we know it's usually going to be type def to a size T, and that's it, and it's going to work. However, what about a humongous data structure? And somebody wants a vector that can hold 8 trillion objects. There's no data type in the language that can support that directly. So there's sort of the hook built in to make difference type be a type def for some custom type, maybe a class type with extended precision ints or something, that could hold that number. So this is the official way to do it. So how long did it take to explain all of that? We don't really want to, it isn't going to affect anything we do. But that's the correct way to do it in old C++. All right, so the first thing I'm going to do is show you what the user code would look like in C++11. So the first thing, which we'll spend a lot more time, this feature, discussing in the second half of the pair of courses, is brace initialization for vectors. Yay. So now I can just do that intuitively. The auto keyword, we know what the type find null returns is, and the compiler has to know what it is here. C++ requires that a function is declared before you use it, one way or another. So if the compiler already knows, why do we have to write it out? Why can't we just let the compiler look at its internal, declaration of find null and know what it is it's supposed to be returning? So there it is. It's whatever find null returns. That's what CIT is. Now, over the last several years, I've heard some debates about whether that's a good, because after all, now you don't know what it is reading the code, right? So in a way, it's kind of hiding information. I think the general consensus now, the dust has settled on this debate, this is better. So we'll just leave it at that. And I'm sure you can Google some of the debates about that. Auto is better. All right. So nothing much has changed here until we get down to where we do the difference type again. The compiler knows what the result is going to be of subtracting 2 of these iterators. So let's just let the compiler figure it out. Yes, question? Why isn't it a null pointer? Because I haven't taught null putter yet. And that's coming up shortly. There's a few places where I kind of jump ahead with a feature before I explain, but they're rare. So this is like one of the only few. Let's say you had a function template, and you'd never write a function template for this, but let's say you had a function template where you needed to perform some type of arithmetic on types you didn't know what they were going to be. So there's 2 types, T and U. We're multiplying them. What's the type of the result? There's no way for the compiler to be able to predict the type of that result in old C++. So you just can't do this, at least not in any correct way. All right, what do you put here, right? So new C++ recycles the auto keyword. It's now not really the same auto we saw before. This is a new application of that keyword. It's overloaded. In conjunction with this arrow operator over here, that gives you what's known as trailing return type. The idea being, once the compiler has compiled this piece of code here, it has the declarations of T and U in hand, and now we can tell the compiler what the return type is going to be as a function of the types of T and U. So what this function returns is the type of the product of T and U. So first, clear, this is not performing a multiplication. Okay? What the compiler is doing when it sees decl type is it's going to be simulating that as if it was generating code, seeing what the type would be of the result. And the result of this whole expression is that type. And it's a compile time operation. And it fills it in for auto. So decl type isn't really officially part of the trailing return type mechanism, but it's a separate feature that they work together hand in hand. I could say arrow int if I really wanted to, and it would be legal, and it would be better because you could just put int here in the first place. But that would be legal syntax, I believe. So it's a convenience feature, or a couple working together. Question?
With the new use of auto, would that break old code that used auto as a keyword for storage?
question is, would the fact that auto's now a keyword that means something else break code that used auto as the equivalent of basically nothing for local variables? Yes, absolutely. So that's an example of a breaking change. But auto's been deprecated since +98. Not a problem. My book. If you've got code with auto in it in the old C style, you're going to have to do a little bit of porting. And you're probably going to be doing that anyway if that's typical of your code base. So it's just one more little thing to. And it'll be real obvious. You know, it's not going to be a silent breaking change, right? You'll get a clear syntax error there. Okay. So here's our first cut at a rewrite of the find null function template in C++ 11. So we'll apply auto and trailing return type. In this case, what are we returning? It's an iterator. So just randomly pick something that has the type of the iterator, c.begin. So just as a quick sanity check, what is the actual type that's going to be returned here? All right, it's going to be the container type : const iterator, right? Because it's a const container. So if you do a begin on a const container, you get a const iterator. That's how it works, as opposed to a regular iterator. Okay. And we go through and do the same thing we did before with auto. Nothing really new here. All right, so that's the first cut. Now, new C++ offers new forms of begin-end that are actually non-member functions. Instead of saying v.begin in this case, you could say begin v. There is no performance benefit to that in this particular case whatsoever. You save one keystroke, the dot. If you're paid by the keystroke, that might be a pessimization. The benefit of this form of begin and end is that it generalizes better over lots of different data structures. You can even use it for old C arrays. So here's an old C array of char stars. And we can apply begin and end to that. And it's a whole lot better than how you have to deal with that situation otherwise, right? You might do a pound define at the top. Size is size of the whole array over the size of the first element, or size of star, one element, you know. That's ugly. And that's what you kind of used to have to do in order to take an old C array and apply it into an algorithm situation. So that's pretty natural. So this is going and finding the first string in there that has a length greater than 4 using this function. As we all know, of course, using function pointers as comparators or as blanking on the word. Thank you. I've had a hard day or two. As a predicate is not efficient, right? So we would probably use a different approach for that, but it's correct. And we're using the non-member end down here. All right, so first C++ 14 slide. C++ 14 adds these pretty natural additional variations of the non-member. So now we can say cbegin, and that keeps us, if we have a non-const container, we want a const iterator, that keeps us from having to declare container : const iterator. Now we can just use auto, right? And use cbegin, and it works. Question?
I don't want to derail the whole conversation, but is there a preference for saying STD : begin versus saying, like, using STD begin and then pulling in begin via?
Yeah, that's completely the question. Is there a preference to using the standard qualifier in your code versus not? Well, two separate issues there. Number one, I have specifically not used it on these slides just to save space. That's not neither here nor there. In the general case, it becomes a matter of style, really. I mean,
I think it's more than style. When you do something like, is begin something we should expect to have arguments in a lookup workflow? Or is that something that something that you would want to say, okay,
I see no would ADL apply here, and I see no reason why it wouldn't, sure. And anytime you have name scoping issues, it's always a can of worms, and you have to be careful. But that's always true. So you kind of trade off having code have the highest percentage of being correct using qualifiers everywhere just to make it really clear. And like Scott Myers loves to do that in all of his slides because then there's no question of what something means, right? Very short. I personally try to avoid typing as much as I can. So I use the using namespaces at the top, which is awful style. It's horrible in production code. If your programs are one slide long, it's okay. So, and then there's a continuum in there. So, in old C++, we have this idea of null pointers, even in old C. But what does it really mean, and how does a null pointer look? How is it declared? There's a question of how the symbol NULL is actually pound defined in your libraries, because over the years there have been various approaches for various reasons, from zero to zero cast to void star to other stuff. And if you see a naked zero in your code, is the programmer intending that to refer to an integral magnitude of 0 or a null pointer? And usually it should be clear from the context. But when it's not, that's difficult. Plus it leads to ambiguity. So here is a situation where you run into ambiguity. If we have two overloads of a function named f, one takes a long, one takes a pointer to char. If we call f and we specify a parameter of 0L, that's a direct match for this one, the compiler is happy. If we say f of 0, though, that's ambiguous, and you get a compile error right here. So nature abhors a vacuum, right? Compilers abhor ambiguity. And if you're lucky, your ambiguity will come in as a compile error right away. Templates get a little bit more complicated. Anyway, we can then specify which we mean by casting, static cast, or in this case, style char star parentheses, probably okay. Anyway, that is required to disambiguate. So new C++ introduces a new reserved word, nullputter, lowercase. When you use nullputter, it can only serve as a null pointer. It can't be used as an equivalent for an int 0. Unless an int 0 would work in a context where a null pointer is required. So if we have these same two functions up here, if we say 0L, it's the same as before. It still is an unambiguous match for the long. If we want to call this one, we just say f of nullputter. This is an unambiguous match for that one. And that's correct. And if we go back to saying f of 0, that's still ambiguous. So good style is take all the zeros that are meant to be null pointers, change them to nullputter. And maybe it'll expose some errors or at least some questionable constructs in your code. So here's the last version of find null I'm going to show you, and I've finally put the nullputter in here. And if I were showing you the client code, I would use the nullputter in that initialization list for the vector as well. But I'm not showing you that. All right, so any questions on any of that? Yes?
Just because I've been away from C++ for a while, it's not okay to do a test for not star ID. Would that be the same as null pointer?
The question is, can you use the not operator to test for a null pointer by saying if bang star IT? That would be perfectly okay. But then that brings up style issues as well, because the not operator, if I see it being used, I would hope it's used in a true Boolean context. So if I was reading a piece of code and I had a Boolean flag called error has occurred, right? If bang error has occurred. That naturally reads if no error has occurred, right? So I kind of shy away from using that to test for IO stream failures or something, unless I'm writing a quick and dirty hack, and then it's less keystrokes. But in production code, I would probably go to something that's a little bit more explicit. So if somebody's reading the code, it self-documents, right?
I mean, the argument against that though is that you have far pointer type thing for then asking how the non-operator define it, how the operator then consistent, kind of nice to have.
Yeah. Ultimately, I'd have to put that into the category of things I would call religious issues. The question was, sorry, but library facilities have built-in operator bang defined, so that kind of, presumably that's to encourage you to use it in that context, right? So maybe for those classes it's okay if that's the convention and everybody's familiar with it. Yeah. And it might indeed generate better code, which is a good reason to use it. Okay. So in C++ 14, we now have yet another use of auto. A function can be declared as returning auto. And there's no trailing return type. So what this tells the compiler is it's going to figure out what the type is supposed to be and just fill it in for you. Isn't that handy? So it actually looks down here at the return statement and figures out what the return type is going to be. Now, it's not 100% across the board always applicable. If you have multiple return statements and they return different types, this doesn't compile. The compiler isn't going to try to guess which one you want to convert to which other one. So if you have that situation, you really need to put the type here and then let the compiler do the conversions as it would normally do. Question?
Well, the observation, that's not really different from a ternary operator. Compiler already has to deduce the type of a ternary operator based on the true-false operands. And so there's already logic in the compiler to figure
Okay.
that out.
So the comment is there's some similar functionality in the ternary operator, the question colon operator already. Yes, that's it within a single expression. So you have a domain that's a little different than across, an entire function. But yeah, there's parallels. There's a lot of features in the language similar to something that happens over there. And who knows what's going on internally, though? Until you actually look at all the places in the standard where those things are discussed, you might find there's some really subtle differences there. But you can't argue this is a convenience feature that's nice, right? Just yes.
In this case, at the call site where you're calling this function, does the whole function definition have to be available? That the compiler can check what you declared to hold the result of the function actually matches what it will return?
Oh, by the time the compiler is processing that call, it will have filled in that type.
But if
So,
you're only,
yeah, okay.
if the call site is only looking at a
Right.
header that just has the declaration,
Yeah, I don't think you can do it in a header. If there's just a declaration, you can't do it. So no, it's simply not, yeah. I can't possibly know if it's just looking at a header file and all it sees is this one line with auto. It can't possibly know. So there's limits to artistic freedom here. And I'm trying to remember what the question was so I can repeat it. What was the question again?
just whether the whole function body has to be visible.
Okay, so yeah, so the question was, in a header file, how would this work? So my recollection is it doesn't in that context. So here's another C++ 14 thing. In C++ 14, there's actually two sort of different families of functionality for specifying a return type of a function with that forward reference mechanism. So we looked at one, which is actually using the auto keyword there, and the auto can be decorated. There could be consts and ampersands, and right, you can say const auto f, that out. The thing to understand about that is the mechanism the compiler uses to deduce that type is virtually the same as the template parameter type deduction for function template parameters. So if you know those rules, it's the same rules that apply to auto. There's another approach called decal type auto. So if a function is returning decal type auto, you can't decorate it. You can't say const decal type auto f. All you can do is say decal type auto. And this employs decal type deduction, which is new for new C++. And it's pretty much exactly what you put there. Whatever expression you have at that return site is exactly what ends up getting put in as the return type. So those two mechanisms, you have a choice which one you use. Sometimes this is good enough, sometimes you need this one. And that's all I want to say about this for right now, because I'll spend half an hour talking about why those two exist. But at least you've seen that they're there, right? That's the idea. Okay. So a new topic. Here's a piece of code in old C++ that's iterating over either an array or a container. So typically you have a for loop with a variable that you initialize and you test and you increment, right? If you have a STL container, you have a for loop where you initialize the iterator and you test for some end condition and you increment it. Here's another example of that. So anytime you have to write all your own loop, there's all sorts of potential for errors. Off by one errors, typos, etc. But in old C++, that's really the only approach that was provided. And if you write a function call to do it, then in the function someone has to write a handwritten loop. In new C++, we have the range-based for. Okay, so now I have an array of ints, and I want to iterate across that sequence. I can just say for, and I can declare it as an int, but I think you'll start seeing more and more opportunities to use auto tend to be taken advantage of. For one thing, I could decide to change the type of int later. This code remains correct, so that's pretty cool. So for auto I, basically declares I internally as like a loop variable, and it's the same type as the type of the elements of the array, and it assigns each consecutive element to I and then uses it. So this is, from this syntax, this is absolutely a value semantic initialization and assignment. So it's always going to be copying the values in. For ints, that's great, right? If copying is bad, if you have some type of larger sized elements, then you can do it by reference. You can do it by reference to const. Again, you can decorate the auto, and it works. So in this case, we're going to actually modify it. So I'm mutating loop, modifying each element. So we don't want a const there, but we want it by reference. And we can have both by reference and const. And this is a little sneak peek for a feature known as initializer lists. So this is an anonymous array of ints, basically, that the compiler just plugs in there, and then we can iterate across that sequence. In these slides, these are all constants, but they don't have to be in the real world, right? They can be variables. Now this one's pretty easy to explain. In old C++, if you have nested template specializations, you were obliged to stick that space in there, or else the parser would see that as a double greater operator. Now you don't have to. Any questions? All right, that's an easy one. All right, so how many of you ever used the old assert macro from the C library in your code, right? Handy, right? It's a runtime sanity check or debugging aid. At runtime, when this piece of code is encountered, this expression is evaluated. If the expression is true, it's a no-op, except for the time it took to evaluate it. Code continues. If it was false, it stops the code right there with a nice little diagnostic saying assertion failure, and it'll typically show you this text because it's a macro. So it has saved this literal string as part of what it displays when that condition happens at runtime. And it'll give you the file name and the line number because it uses predefined compiler macros for that. Great for runtime. But what about if you want that sort of thing at compile time? If you want to be able to say, I'm testing some compile time condition, and that means it has to be formulated completely out of constant expressions, and you want to bail out of the compilation, or at least make a fatal error so it doesn't continue on if some condition has occurred. So now we have that. It's called static assert. Yet another overload of the static meme, right? I'm not going to call it a keyword because actually the keyword is static underbar assert. But how many places is static used? It'll never end. There'll be 8 more in C++ 17. Watch. Anyway, static assert and then a condition. And the compiler has to be able to evaluate that condition. It has to be formulated out of constant expressions. If that condition is true, it's a complete no-op, generates no code, great. And if the condition is false, it generates a compiler message, a fatal error. But it'll continue compiling, so you get other errors to deal with as well. And you know that something happened. So here's a couple of examples of how you might want to use this. Let's say you want your code to be confident that you're running on at least a 32-bit machine. Because you know if you try to compile that code on a 16-bit machine, it's not going to work right. So we just have a static assert, and the assertion is the size of an int is greater or equal to 4. That's a compile time constant expression. Size of is always a compile time expression. All right. And if that's true, nothing happens. If it's false, you'll get this message, and it represents a fatal error. Here's another use case. And I based this example on a piece of code Steve Dewhurst wrote a while back. This is way before C++ 11. He was trying to find a way to make code a little bit safer by diagnosing attempts to shoehorn variables that don't fit into each other. So if someone attempted to assign a long into a bool, which is perfectly legal, it's perfectly legal to assign a double to a bool in C++. Isn't that lovely? So if you wanted to be able to diagnose that sort of thing, whether or not it would actually work, you just don't want to allow it, then there's a way to write a template that in old C++, it would be a runtime situation where if the size of the result is greater or equal to the size of the expression, then, let's see. Okay, so if it's true that the result size is greater than the size of the original expression, that's good, and it'll be silent. But if that's false, that means it's possible it won't fit, and that's all you're really concerned about, just the possibility it might not fit, and it would basically throw an exception or something in that case in Steve's original code. So now we can take it and make it completely compile time, which is really better because you can detect that situation at compile time. The compiler knows the size of these two relative types. So you get the error if someone attempts a potentially unsafe assignment or conversion. Otherwise, it'll do a static cast and return the correct result. So in use, if I do a safe cast int from a long, depending on what platform you're compiling on, that might be okay or it might not, right? If you're on a 16-bit machine, this is going to fail. A long will be 32 bits and int 16. If you're on a 32-bit machine, they're both the same size, typically. At least it has been typical for a long time. And it'll be okay. And certainly if a long is bigger than an int, it's going to, oh, right, then it's not going to be okay. So here's a case where it'll always fail. You can never shoehorn a long into a character. So any questions on static asserts? Okay, straightforward. New topic. So when you use templates a lot, there is a long-standing issue with code bloat. It comes in many guises. One guise is simply that an incredible amount of code is generated by the compiler and then thrown away. So if you have a large code base, maybe hundreds or thousands of source files, and you use the same templates a lot and you include them in all of your modules, in old C++, the compiler was pretty much obliged, using the inclusion model anyway, which was what most compilers have used for a long time, was pretty much obliged to instantiate all member functions of those class templates that were actually used in each individual module. So if you have 1,000 modules, it might generate the same code 700 times for a pushback type of function or something. And then the linker throws all of those away at link time except for one. And that's considered the proper behavior. So code bloat just during the development phase. So we're not really talking about code bloat at execution of the resulting object code. And that's the situation that the C++ Standards Committee attempted to address in the original C++ 98 standard with the export keyword. So the export keyword kind of pays homage to the fact that the very first implementations of templates actually did do separate compilation of templates, just like we do separate compilation of functions and classes, and then we link with them. And there's still development environments out there probably that do that. So the Standard Committee wanted to give the blessing to compiler vendors to use that approach because it might lead to one solution to this code bloat problem. However, and this was a hard lesson that the Standard Committee learned, they didn't actually have implementations written yet that did it. And the committee just assumed, well, compiler writers are smart. They'll figure out how to do it. And the compiler writers themselves on the committee probably thought, we're smart. We'll figure out how to do it. And approved this feature. 3 years later or so, the first actual working implementation was completed by the Edison Design Group. And the conclusion that they came to was it wasn't worth it. The actual savings of development cost overall was not significant from all the work of doing this separate template compilation. And the reason has to do with the way templates are processed. Two-phase translation. Compiler has to process the raw template source code once to do just a sanity check on the code. And then when a user specializes that template at some point later in the compilation, then it kind of has to go through everything again, and this time actually plugging in the type and checking the sanity of the expressions in the template and generating code. So what's the real benefit of separate compilation if compilation requires going in and looking at the result of the previous separate compilation anyway? And that's what led to the realization this wasn't really a good solution. So there's a great backstory behind this. The guy who actually spent 3 years of his time implementing this is on the Standards Committee, and told him what was going on. And the committee, felt bad he went and did this. And they wanted to deprecate export for C++ 14 because it was clear, it wasn't really a great solution. And the guy that actually wrote it insisted it not be deprecated, but completely excised from the language, because there was no real benefit. I mean, they would have been doing it as a personal sort of nod to him for his effort, right? And with his blessings, the committee actually removed it completely. So it was introduced for 98, completely eradicated. So it's an error to use export in C++ 14, 11 and on. All right, so that didn't work. Fortunately, there is a solution. And it's amazingly simple. So I don't know the story about whether anybody thought of this before. I would guess not. In C++ 11 and on, if there's one of those templates that is going to be used heavily across an entire project, then after you include all the header files, basically in each translation unit somewhere at the top, you say extern and then show what would normally be an explicit class template specialization. So this syntax, except for the extern, was already in the language. And it means fully instantiate that template without regard to whether the functions are actually used or not. But remember, this is in the compilation process, not linkage. So each translation unit where this line appears would generate a full set of all the member functions of the class. Okay? With the extern keyword, it inhibits the instantiation of any member functions of the class. So you're basically telling the compiler, don't worry, this will be instantiated elsewhere. Elsewhere meaning typically in some other translation unit. So if you've got 1,000 modules in your application, 999 of them will have that. The 1,000th one will probably still have that, and then it'll have this in the CPP file. And that will generate all the functions. So there's exactly one copy of all those member functions generated, and it's used by the entire application. Question?
How does this work with auto?
How is it? Question is, how does this work with auto?
Yeah, the written type of
Those are completely independent features, and I can't even begin to grok how to answer that. So, I mean, auto has its set of rules. This is a separate mechanism.
I mean, like, when you have a method in the vector, you take it as nothing. Then, okay, no, what's the
Okay, so
method?
the question is if you have a method in the vector which returns auto. We actually talked about before. We were just talking about auto. And the answer is you can't have a declaration of auto in a header file if that's all there is. You can if it's an inline function, right? Then it's fine because the inline function has to be fully implemented in the header file, or by convention, that's where it's going to be implemented. But it's an ordinary non-inline function, and you're just showing a function declaration, whether it's a template or not, that's illegal for the deduced function return type. Okay? But it has nothing to do with this mechanism. They're completely independent. Any other questions on extern templates? Okay. Now we're doing good. How many of you program in Java? Or just know Java? Just a few. Okay. So Java and C++ had very similar exception handling syntax. And in Java, if you declare a method, you can declare what sort of exceptions it throws. C++ 98 has that same feature. The syntax is a little different, but the meaning's the same. It's the throw keyword. And in here, you put a list of exception types that function throws. But there's a serious difference between the way this declaration is handled in Java versus C++. In Java, that specification is 100% enforced, always. So if a method says, I'm possibly going to throw exceptions 1, 2, or 3, all callers have to explicitly deal with that. They either say they're going to rethrow that exception, or they have a try-catch where they catch it. Has to be one of the two. Okay? And that's actually nice because everything is self-consistent, no surprises. That's not how C++ works. In C++, you have a list of exceptions in this throw clause. There's no requirement of the caller to even know that those exceptions might be thrown. No requirement. So the whole point of it is kind of lost. And then when you throw templates into the mix, it gets really ugly. Because if you have a function in a template, how can it possibly know what sort of exceptions are going to be generated on operations on T objects? It doesn't know what a T even is. It doesn't know if it's an int or it's some complex type with all sorts of member functions that throw exceptions. Well, as the language evolved, even for C++ 98, the committee realized there's no use for the throw syntax when you have an exception name in here. And the only form of it even used in C++ 98 is this exact one where it's empty. It is useful to know that a function is not planning to throw any exceptions. That's really what it means. This says, I don't plan to throw any exceptions. So if code in swap actually does throw an exception, it terminates the program. So that's the way it was in 98. And it wasn't really all that useful. It did allow certain types of optimizations to happen based on whether or not there's potential exceptions that are going to escape. Basically, what it did was add a lot of responsibility to the compiler to check what's going on inside a swap or any function and make sure that if there's an attempt to throw an exception, and for that exception to be emitted from the function, that it translates it into a different type of exception and ends up terminating the program. So it actually just made the code less efficient. Okay, but that was a price people were willing to pay because it was good information to know a function isn't going to emit an exception. All right. So that form of throw keyword has been deprecated for C++ 11 and on. So don't use it anymore. The new version is called noExcept. So the keyword noExcept says this function does not throw an exception. And it's kind of equivalent to this in terms of its meaning, but internally, without having a list of potential exceptions to have to maintain, the code that ends up getting generated from the use of noExcept is going to be more efficient than it used to be from the empty throw clause. So the simple noExcept says, I'm never going to throw an exception. And for something like swap, you might be able to safely say that. If you know the types, in some particular case, you can be confident that every type of T you specialize the myContainer class on has a non-throwing swap. You can basically be, or all the members of T have non-throwing swaps. This can be guaranteed to be a non-throwing swap as well. If some piece of code inside of a function like this does actually try to throw exception, again, it'll terminate the program. Yeah, question? Question is, will it tell you where you were? The error reporting for exceptions in C++ is really dependent on the implementation of the system that you're working in. So first of all, there may not even be information in an exception, because an exception is an object. And when the exception is instantiated, if it takes the trouble of actually encapsulating some information, then where it's caught, it can be examined and diagnosed. But if not, it won't. So if you want that facility, if you want it to give you good information when an exception is finally caught, you have to build that into the system yourself. You're not going to get an automatic backtrace like you would in Java. Make sense? Pardon? I believe so, because the runtime system will actually see the type of the object, and using RTTI, it should be able to diagnose that type, right? But if you want detailed information, like the location of the throw point, you have to actually code that functionality in yourself. Maybe your development environment in debug mode does that for you already, right? There's always that situation. But in release mode and with optimizations, if you haven't planned to do that, it's probably not going to be there. Question? I believe the question is, will you get a compile time error? Do you get a compile time error? I believe not. It's of use for performance reasons. Because of move semantics, there's all sorts of things that happen when you're moving objects that cannot be done efficiently if there's potential of an exception to occur during the move. So this is really all tied into move semantics, and we'll be discussing that this afternoon. Okay? So really, if it was just a matter of replacing throw, open, close because it's a cleaner syntax, that wouldn't probably be sufficient in and of itself. But it's more than that. It really covers several different areas of importance in the whole process. Okay, so sometimes you can't just say noExcept. You might not know. You might have some functionality in your function implementation where you're using template parameters, types like T1 and T2, and you don't know what their behavior is. So this is the problem, back in old C++, there was no way to declare what exceptions you're going to throw because you don't know what sort of types you have. With noExcept, there's a workaround. noExcept can be conditional. So the one syntax, the simple syntax, was just to say no except. This is equivalent to no except open paren true close paren. If you use no except with a parameter, a parenthesized expression, it has to be a Boolean expression, and if it evaluates to true, it means no except, and if it evaluates to false, it means no except, or except, I guess, which is not a keyword. Okay. So as an example, let's say we have, and this is actually out of the G++ library I had on my machine at the time, with some complexity stripped out. But this is the essentials. If we have a pair class template, which is the standard pair, 2 items, first and second, right? And we want to have a swap function, is it safe for this to be declared no except? Well, we don't know, because we don't know what the types are of first and second, and we don't know if trying to swap those is a no except operation. We can actually express that. This swap is no except if swapping the 2 firsts is no except, and if swapping the 2 seconds is no except. Then the whole thing is no except. Question?
Got another ADL question here. Swap here, the ones you're referring to in your no except expression, how do you know that it's the same swap as in the body, right? Because you're saying using STD swap, well, sure, that might pick up a different swap than the one in the expression itself. So the no except expression versus the body function.
So the question is, down here we're saying using standard swap, and it's clear this swap refers to the standard swap. What about this swap up here? It's really beyond me to be able to answer that. I'll just say that right out. I'm sure there's an answer. Does anybody happen to know? Often there's a few standards people in the room or
Yeah,
whatever.
if there's
Okay.
like a normal accepted way to deal with ADL in these decorator type.
I've never thought about that whole aspect of it. It's a great question, though, and I'm going to make it a point. Come see me after.
Okay.
All right. So good questions. But again, this is an overview, not a deep dive. Yes?
So if you, for your no swap, say you naively implemented this swap and you just said, okay, I want my swap to be no except.
Mm-hmm.
But then it turned out that the second, say, actually, the argument for second swap did throw an exception. Would the compiler catch that and say, you declared this no except, but the template type that you passed in actually
Right.
does.
Okay, so the question is, what if you lie? Okay, and I believe what will happen is a runtime, termination when that exception tries to emit out of the swap. If you've declared swap no except, you just say no except, and then something actually throws an exception, it terminates. That's it. And the compiler, maybe it's a quality of implementation issue. Maybe some compiler can figure that out at compile time. I don't know. It's not obliged to, probably.
External tools.
Yeah. Lint. Question?
Are there any flags that you can just turn no except out for everything?
The question is there some way to just blanket make everything be no except?
Some apps just don't use them.
I don't know, but that sounds like a completely bad thing to want to do. Because most things in your program, if you use templates, okay, exceptions are going to happen. Exceptions are not bad, okay? When they happen, that's information. You want to know that something went wrong. And it may not be possible to refactor your entire code base to make sure no exceptions ever get thrown. I don't think that's useful.
It makes it insane. Like, you can do it.
Okay, so somebody knows.
Because you said that later on you're going to talk about, from the move point of view, for performance reasons, putting a no except there can happen. The exception's still going to happen if it comes through at a runtime issue.
Right.
So if you're not planning on having any exceptions, because you don't code with exceptions, then it seems like you marked everything no except, you get the performance boost, and you still get the runtime exception if it happens.
Okay, so the question is, wouldn't it in some development environment be a useful thing to simply standardize on not allowing exceptions to ever happen, have the compiler enforce it? Okay, if you conclude that that's a useful thing, go for it. But in the general case, you're going to be working with code from the library, which throws exceptions. You're going to be working with other libraries, and there's exceptions.
So it wasn't quite the question.
Okay.
The question wasn't, can I get rid of exceptions? The question was, could I label all of my functions that I'm defining
exceptions by default.
Right.
Because I know that they don't, and the ones where I'm gonna be handling third-party code or library code outside my graph are going to be captured.
Okay, so for whatever reason, the question is, can I just declare to the compiler, I want all my declarations of functions to have an implicit no except? And we've already heard there's a GCC option that does that.
Yeah, that turns exceptions off, doesn't change your functions. All of it.
Yeah.
Yeah, so it's two different things.
So I don't know. That's too deep a dive. Question?
Yeah, you can do that because your translation unit is going to include standard library headers, which can be compiled if they are not no accepted. So if you have something that automatically turns on no accept for everything, you would know what's your code, what's the standard.
Right. The comment is if you mix in code from the standard library, but your code is all no except, but standard library code isn't, it's a mess. So. Simple answer, I don't know. All right, so let's move on so we can get these features handled. Problem. How do you average n values where you don't know what n is going to be up front? Seems pretty simple. So it turns out in C, there's a way to do it. You write a function that has its first parameter be a count, and then you just provide that many values, and you can make that work, as long as the user actually passes the right number of objects of the right type. And you know what type they're supposed to be. So a function to average some unknown number of ints can be written. A function to average some unknown number of doubles can be written. But there's no type checking on those parameters, on those arguments. As long as the user passes nothing but doubles and provides the right number, it'll work. And if not, undefined behavior. But you have to write one for every different type. So, not the greatest solution. We can't use default arguments in C++ because a function with default arguments has no information once the body's entered of how many were actually provided. So you can't do an average if you don't know how many numbers were actually provided. Overloading and templates provide some options, but they're ugly. So there's really no good way to do this in old C++. But now there is. So the mechanism that makes this kind of thing possible is called variadic templates. And by the way, in C, these are called variadic functions. Right? Variadic meaning a variable number of parameters. So in C++ 11 and on, you can do that with templates. Everything happens at compile time, and it's based on a recursive model. So in recursion, right, you have a terminal case, and then you have the general case. So fib_o of n is fib_o of n minus 1 plus fib_o of n minus 2, or whatever, right? And for the special case of 0 or 1, fib_o is 0 or 1, or whatever it is. So with variadic templates, you have, and we're going to use sum as the example here. We just want to calculate a sum of some unknown number of values. So we'll start with a terminal condition. We assume you provide there's at least one, and nobody's going to try to sum up nothing. If you want to be able to handle summing of nothing, I guess you can build that in. Let's not worry about that. So summing of at least one value, n is n. That one's easy. The general case is the sum of one argument of type t and some unknown number of additional arguments of unknown types. Notice this is a template. It's variadic templates. It only works for templates. Up in this template parameter list, there is a parameter pack. Type name ... introduces a parameter pack, and we'll call it args. That's just the symbolic name for that set of types. So internally, the compiler will have a parameter pack up here, which will look like int, double, double, int, whatever. Then the function also has a parameter pack, but this is a function argument parameter pack. So internally, this will be a set of expressions. And the compiler will have that pack internally as x, 37, square root of 18, whatever, well, whatever the result of that is. So the thing is that these two have the same size each, and they remain in lockstep. The compiler treats them as a matched set, like a zipped up set of two items. type and expression. Okay. So if I want to sum up a single value of type t and an unknown number of additional values, then all I have to do is add the initial parameter to the sum of the rest of them. So I can take this argument parameter pack and expand it by saying name dot dot dot. Right, so if there's, let's say, 7 values, then the initial match of this call will be to this function template, where the type of n is int, and this parameter pack has a size of 6. It's the 6 remaining arguments. And it'll be a recursive call to one with a parameter pack of size 5. A recursive call. Eventually, it'll call that one, and then unwind. And all this happens at compile time. So the actual code generated is, it'll load up a register with the sum of those numbers and display it. And it's never actually doing addition at runtime. Question?
This doesn't restrict those at all.
We'll get to that. This is the simplest case. The next example is they're different, well, there'll be different types.
I mean, you could add the integer of tools.
Yeah, the question is, can they be different types? Yes, they can, but there's a catch. So we need a couple of slides to deal with the catch. Okay? Question?
Is the dot 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 token all by itself, or is it somehow combined with the others?
The question is dot 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 a token? Yeah, it has to be. Is it somehow combined with this? Yeah, so I don't know how the compiler looks at it.
I'm
But
just wondering, like, you don't have white space between the dots and the thing on the left of it. If you had a white space, would that?
question, if you put white space here, would it work? I suspect it still would, because it's still a token stream. There's an identifier and then a token dot dot dot. And it doesn't care if there's white space in between. So because this isn't any kind of a reserved word, there can probably be white space there. I'd be really, really surprised if you can't put white space there. Let's put it that way.
There can be white.
Thank you. There can be white space. My intuition was correct. Having written the compiler helps sometimes. Okay, any other questions? Okay, because we've got a lot more to do with this. This is just the start. So here's some examples where the types are all the same, right? And you expect that's going to work. Now we're going to hit a hitch. If sum is called with a mixture of different types, you can get the wrong value the way I have coded it. So here's an example. If the client says sum of 1, 2.3, then this match will have the type of t be int, and eventually this will go back to the 1arg version with double. However, we have now shoehorned the result, no matter what the additional arguments are, to be an int. That's bad. I'm not sure if it was last year or the year before. I didn't realize that. And the slide was up without any attention to this issue, and somebody pointed out, but it'll be wrong if there's this order of parameters. And we spent a while figuring out, and I'm going to show you the result of figuring that out right now. Okay, so one solution to this problem, or the solution to the problem, is trailing return type. We just use auto and trailing return type. The return type is the type of adding n to all the rest. Whatever that is the correct type, right? Yes, that is correct. Unfortunately, this doesn't compile. And the reason is really, really, I don't have any safe for work terms to use for what it is, but it's a problem. The recursive reference to sum is illegal because the compiler at this point does not know the full type of sum yet. It's still in the process of evaluating this header line which says what the type of sum is when it sees the recursion. So the natural result there is, oh, that means we can't do it. Well, that would be true except for something else. That restriction only applies if it's a member function. If it's a non-member function, that restriction doesn't apply. So all we have to do is make these functions be static functions of a template class. So here it is. Actually, I didn't say that right. They have to be templates, static function templates of a class. Yeah, that's pretty much the correct reaction. It's too bad you have to do this. But this solves the problem. All right, so now we have this static version of sum here, and we have static version of sum here, and the logic is the same, except it's a static function versus an ordinary non-static number function. Now it compiles. What about just a free function? I suppose that would be okay, except the whole idea here is these are related, so you kind of want to put them into the same namespace type of thing. So if it wasn't in a struct, I think you could still get away with it. Then you got all these free file scope functions. You really like that better? Okay.
Wasn't that what you had on the previous slide? Wasn't that a free function?
Okay. Yeah.
That's a free
Oh no, but this I'm just looking at this and I'm looking at this out of context. Okay, we're still assuming this is part of. Ah, actually, right. These are all separate functions. So, do they have to be in a struct? You know,
Because go back one slide.
I never thought about that, but there's some reason I think they need to be inside of a type. Yeah, there's.
Oh, okay, that actually makes sense. That's so obscure. Okay.
I can't tell you why, but I believe it has to be in there. I'll try it without being in a struct. We'll see what happens.
You could introduce another sum in another like header file to the free function.
Yeah.
Struct sum, you close the entire scope of how you can define sum. If you had free function sum, then header 1 can like define its original one, and then header 2 can define another sum.
All right. So the comment basically is there's all sorts of scoping craziness that can come in, maybe even ADL to mess all of that up. Anyway, that works, so that's a good thing. We have a way that works. There may be other ways that work too. Well, now we can move to average. That was the whole point of this, right? To write an average function. So here's a variadic average function template, and it relies on sum, of course, to calculate the sum, but then it has to divide that by the number of things that you've summed. Well, conveniently, there's a size of ... operator specific to variadic function templates that is equal to the number of items in that pack. And that's exactly what we need. And it works. And now you can mix and match your types in any order. It just works. So it is a solution to the problem.
And that's figuring out all those averages at compile time. If there were.
Well, because they're constants. The question is it doing this all at compile time? Absolutely, it's doing it in this case because these are constants. And if they weren't constants, it would generate the appropriate code to do it at runtime. Okay, I've just kept the example simple by using constants. Then I don't have to show the declarations anywhere.
It's basically just been a concept for analysis.
Yeah, it's doing. It's definitely doing a compile time reduction of expressions as constant expressions. All right, so const expr. New feature enables compile time evaluation of functions, including operator functions, constructors, as long as every expression in the function is a constant expression. And there's a difference between the C++ 11 flavor and the 14 flavor. So let's look at the 11 flavor. Here's a function template, square, that takes some value x and returns its square. So it's declared as a const expr. Now what that really means is this can have two different existences. It can exist in an environment where, in fact, this is a constant expression, and it can also serve as an ordinary function to work with non-constant expressions. So those are two different specializations. To prove that, I'm going to create an array of widgets, and size is a compile time constant, so that's always legal. But I can make the dimension be square of size. This compiles. The compiler plugs in size into square. It figures out that can, in fact, be a const expr. So it does the math at compile time and plugs the value in. No runtime cost, except for the space for the array. All right, here's a non-constant expression. So we can't just declare an array using val here, right? That's an error. Int val squared equals square of val. this is a legal expression, but it specializes into a non-constant expression function. So this ends up behaving as an ordinary function here. But here, using val, it's an error. All right, so this is an attempt to take the result of square, and the compiler knows the result of square is a non-constant expression because val is a non-constant expression, and then the attempt to use that as an array dimension is just an error. Question?
Was there discussion about not requiring a const expert decorator? I mean, it looks as if the compiler could have inferred both those cases, you know, by what it had already.
Question is, can compilers be smart enough to just know, without even declaring const expr, have them behave as if you did? Presumably, that's an optimization that's possible. Lots of things like inlining started out as absolutely explicit and have sort of been migrating toward being implicit. In 10 or 15 years, you could probably write your entire code base without ever using the inline keyword, and the compiler will inline everything it possibly can. So it's a quality of implementation issue. It's a compiler technology evolution issue. Right? So there's certainly nothing preventing a compiler from optimizing this, if you didn't put const expr in, from optimizing it so it still behaves that way. But in terms of generating error messages, it's sort of obliged to give you an error if something's a non-constant expression here, right? But if it is constant, it can optimize based on that. It probably would. Question?
Wouldn't the compiler give you additional error checking inside of the square function if you did something non-const expr-ish inside the implementation of square? Like if you
It'll turn into the flavor that's not a const expr. So if I took x and multiplied it by z, where z was a global variable, it would become a non-const expr function. It's like it's like Schrodinger's cat. It's either dead or alive. So, pardon?
It's declared as const expr, and you do something that's not const expr-ish inside of the function. The compiler will say, no, you can't do that, you have to remove the const expr.
So the comment is it won't compile if you do something non-const expr-ish. Okay? So in my head, non-const expr-ish means including something that's, oh, okay. I haven't played with it enough, but I'm seeing if you actually use an explicit variable in here, then the compiler just says sorry. But if this is used in a context that ends up being non-const expr, then it becomes,
You were mentioning
yeah.
going out to a non-constant global.
Right.
Go out to a non-constant global and say no.
Okay. So the compiler does check that everything in here can be const expr.
Yes.
That's basically the rule. Thank you. In C++ 14, some of the restrictions on 11's const expr have been lifted. So in 11, you're limited to like one little expression, no control structures, except you can use conditional operator. You can't have loops. In 14, most of those goes away. Bjarne says a const expr function, now talking about C++ 14, can contain anything that does not have side effects outside the function. So there's a bunch of stuff that applies. Still can't have gotos, or try catch blocks, or call non-const expr functions. So it's a little more flexible. There's also const expr data. Variables and data members can be declared const expr and be initialized with const expr expressions. That's OK. So here's a const expr area, the product of pi, which is a constant, and the result of square, which is, we already know, a constant because double is a constant. That's valid. All right. Where?
Const expr area.
Oh, yes, I'm missing a type. Sorry. So maybe I should have put auto in there. Thank you. Bug. What would a presentation at C++ now be like without at least one bug?
So, putting you on that.
Okay.
One question. So, with const expr, I assume that one of the goals is to try and minimize some of the macros that are something like that.
Anything that minimizes macros is a good thing. So if that's a result of this, who's to complain? I'm not sure that was a primary motivation. It was really an observation that lots of stuff that happens can be done at compile time rather than runtime. So let's facilitate that and provide additional language facilities to support that.
So, I mean, obviously, there's a lot of macros and that side effect. That's a harder to catch.
Yeah. Well, the whole question of how to get away from macros is, I think of that as kind of a separate issue as well. It's always good to eliminate macros. Anyway, I want to try to get to the rest of this, so let's move on. Template alias. So there was an idea proposed way back called template typedef to solve the problem where if you have like a set and you're always going to use a particular comparator and you don't want, you'd like to not have to keep expressing that in your code, having to say standard greater every time. So the using syntax of C++ 11 gives you a way to encode the greater comparator implicitly and just give it a new name. So set greater than, right, is equivalent to saying standard set of t with greater t as the comparator. And now we can just say set greater than double, and it behaves exactly as if you had said it this way. So that's pretty handy. And you can imagine this is a fairly simple example. Imagine a much more complex setup. It can really make the code simpler. And sort of the way that once a new keyword has been added or a new syntax has been added, the committee tends to find ways to overload it or reuse it. The syntax, the using syntax, can also serve as a simple replacement for old typedef. Right? Remember how much of a pain it is to find the identifier in a typedef and figure out what it is? So now you can just say using void func equals that. So these two are 100% equivalent. Same thing. That's the template alias. In C++ 14, you can have variable templates. And as far as I know, this is the one example. It's funny, I've heard Dan Sachs say there's only one good example he's ever heard of multiple inheritance. And that's class seaplane, public airplane, public boat. So every other example of multiple inheritance he's ever seen, he can refactor it to be not using multiple inheritance, right? So far, this is the only example anybody ever uses for variable templates, because this is right out of the proposal. You can have template type name t, const expert t pi, and give it a nice extended precision definition. And then you can specialize it on things like float or whatever, and it would just work. So there it is. I don't want to spend a long time on that one. Some string-related stuff. Now there's Unicode of different precisions. And here's the syntax for specifying them. So a UTF-8 string, UTF-16, UTF-32. Capital U, small u. If you need that, you know how valuable that is. I haven't used them. Raw string literals. Well, now that we have regular expressions in the library, we tend to need to use backslashes a lot. And of course, using backslashes in the old C, C++ syntax is pretty bad. So this is what we were stuck with before. In order to specify things like double quotes and backslashes in a string, you had to do stuff like this. Now you can just say capital R quote open. That's the opening delimiter. And the closing delimiter is close quote. Everything between those two is literal. So if you just cover up that and that, what's in between is exactly the text that becomes part of T. So then the question becomes, what if you want close quote in your string? This is how you do it. You say R quote, an identifier, open. Okay? And then the closing delimiter is close the same identifier, quote. So I believe this can be up to 14 characters, which should probably handle everything imaginable. Okay. Now this is an interesting one. I actually was one of the reviewers for Bjarne's latest version of his seminal C++ book, right? 1,400 pages. And of all the things I found in that book that I had questions about, the only one where we actually went back and forth about 6 times in email, because I just couldn't quite get it, was this one. And he finally convinced me. And it's completely not clear from the standard or from anything anywhere else what's going on here. So I will tell you how I understand this now in 5 minutes. Okay. So this syntax is wrong. Does everybody see why this is wrong? A literal string is immutable. It's undefined behavior to modify any of those characters. So if you define that, assign that to a char star, you're basically giving later code carte blanche to go in and mess with those characters, which is UB. Don't do this. C++ 98 allowed this as a legacy. It put up with it because there was legacy C code that was written before the const keyword was invented. And this was the only way you could do this in C before that. However, it was deprecated for C++ 11. I'm sorry, for C++ 98. For C++ 11, according to Bjarne, and supposedly according to the standard, it has been made illegal. This is now illegal. What I found is every compiler still accepts it. So this seems to be a compiler issue. Compilers should not accept this anymore, certainly not in strict mode. And we tried it, and even in strict mode, compilers were still accepting this. But they shouldn't be, okay? Anyway, don't do this, ever. Always, if you're going to do it, do const char star. This is correct. Now the compiler can diagnose undefined behavior attempts. Question?
You didn't even get any warnings?
Nothing. The question was, did I get warnings? No. I got no warnings. But that may be because of how I have my warnings set. So, yeah, you'd think modern compilers would at least give you a warning, but what I'm trying to say is this is actually now an error. So it shouldn't even compile if you do it. But I haven't seen a compiler yet that actually makes this a fatal error, but it should be. So that's that. This is kind of cool. There's a new quoted facility in C++ 14. Before we had quoted, if you took a string with embedded white space and you just inserted it without doing any special conditioning of the streams, and then you extracted it back, you'd only get back the first word because this is a terminator, right, on an input scan. So if you're an instructor like me and you're teaching a beginning C++ course and people are writing their first hello program, please enter your name, and somebody puts a space in their name, it doesn't work. Okay? So now the right way to do it is use quoted. If you take the string that might have spaces and you put a quoted around it when you write it, and then you put a quoted around it when you read it back, it'll come back as it was written. It works. It's kind of cool. 14 only. Question? I'm not sure if it's a language thing or a library thing, to tell you the truth. Is it a library thing? Okay. So sorry, it shouldn't be in this talk. I missed that in my excision of library material. All right, here's a real language feature. This is nice. Inline namespaces. So let's say I have a company, BDsoft, and I have several different versions of the user facilities I'm providing to people. And I put each version in a different namespace. You could do that, back with C++ 98. However, now you can declare one of those with the inline keyword, and it implicitly hoists all the names here up into the top level BDsoft namespace. So it makes this the default implementation. And the nice thing about this is versioning. So presumably this is an ancient version, this is the current version, this is an experimental version, and at some point this is going to become old, and this is going to become inline, and then there'll be a version 4 that's the experimental one. And so as a library provider, I can just move the inline. Presumably the functionality will not, there's no breaking changes, right? That's a separate issue. And clients will immediately gain the benefit of all the improvements in the new version without having to change their source code. They will have to, of course, recompile. But that's a nice facility. Any questions on inline namespaces?
How does that affect, or how does that appear in linkage with the mangled names? Does the namespace v2 still show in the mangled name?
I'm trying to remember if namespace names even show up at linked in object files. Aren't they compile time facility? So that can vary. I don't know.
Does this function like an alias, or does it function as if the names inside namespace v2 are also separately defined?
It sort of acts the same way as the using directive when you put it inside of a function, right? If I say using namespace foo in a function, it behaves as if all the identifiers from foo were declared at file scope. So what this does is it makes it behave as if all the names in here were declared at BDSoft scope, as opposed to BDSoft : namespace v20 scope, which they'll be there too. They'll be in both. Okay?
So it would be equivalent to not saying inline, but inside namespace BDSoft saying using namespace v2.
Yeah, that sounds right. But you don't have to. Or could I, as a library implementer, could I have simulated this by putting a using up here? Yeah, I don't know. Something tells me if it was that easy, they would have just done that. So I don't know. All right. Oops, somewhere I lost my focus. I don't mean that as a mental thing. Okay. So attributes, instead of having compiler-specific pragmas and stuff, now there's some standardized syntax for saying the same sort of things. The syntax is butt ugly, but there it is. So you can decorate a function as not returning and help the compiler optimize or detect errors based on that. Here's a really useful one, actually. In 14, you can decorate something as deprecated. And if anybody tries to use it, they'll get a warning, which is nice. So that's attributes. I know what happened here. More stuff. Scoped enums. Normal enums, old enums, have a habit of leaking into surrounding scopes. So scoped enums have a specific scope, and an attempt to use them outside that scope is an error. You have to qualify it. And you can also now specify the integral type. So it was locked as int in old C++, and now you can specify some different integral type. Long is there. Self-explanatory. Align as and align of deals with boundary alignment. You can test the alignment, and you can force the alignment of your data structures. And there was a 90-minute talk last year on that, and I got lost after 10 minutes. That stuff gets really complicated. Unions are now allowed to have constructors, destructors. They've loosened some of the restrictions on unions. Of course, you can't have things like something that requires RTTI type support inside of something like that. But there's definitely more flexibility to unions and pods than there used to be. And they're doing their best to try to facilitate what people try to do with these things. There's a garbage collection interface, but no actual garbage collector. It's basically hooks for garbage collection if you really want to use it, and certain applications would like to have that. So I don't know how that works. It's just there. As far as I know, no one's actually, there's no like standard. I guess there's things like the Bohm collector, and it's designed to facilitate that. User-defined literals, I can say, if I have user-defined type, this is different from one coming up in a minute. User-defined type binary, I can tell the compiler how to deal with this, where B is a user-defined, something I've invented type. This is now a bad example, though, because B has become standard in C++ 14. So imagine it's something other than B. You can invent your own. And it's a trick. You basically write a function that takes a string parameter, you teach it how to parse, right? And then the compiler uses that. And that's where const exprs become really, really useful, because that parsing is typically done in const expr mode. Binary literals. So that's a different syntax. I'm sorry, so it doesn't conflict. But now you can say 0B. I've wanted that for a long time. 0B or 0 capital B for binary literals. You can use the apostrophe as a comma. Isn't that great? It just accepts it. But just the apostrophe. It looks like a comma. It's just phase shifted a little. Okay. That's it. Not bad. I'm only 5 minutes over, so we're officially done.